Hello and welcome back, everybody. Today in calculus, we will talk about logistic growth, and that is going to be a continuation from the separable variable that we did in the last section. So, in terms of what this is and what's the application over here, it's basically tying up with the idea of exponential growth. So I guess kind of like back in Algebra 2, you learn about exponential growth, how if you have something like, say, a population, then it grows exponentially over time. And also if you have, like, say, maybe decaying, like, say, if you have an element that is decaying, then over time you're losing like half of its element or amount each single year or every so often years. So we're going to go ahead and look at this part right here. Exponential growth is usually related to the following differential equation over here. dp dt is equal to k times p, which is basically saying that the rate of growth is going to be equal to whatever the current population is, or it's proportional to the current population. So for example, the rate of growth is 30% of the current population. So if you have a bigger population, then that means the rate of growth is going to be bigger because that 30% of a population is going to be a bigger number, versus, like, say, if you have a population that's a small number, 30% of that is going to be something that's going to be smaller. The result is that when you have an exponential growth like this, you're going to end up with an exponential equation. So the curve would actually look something like this then. And we've graphed it plenty of time back in Algebra 2. Now, in terms of how do we solve for this, just to verify that you do get this type of equation, we can go ahead and use separate variables for each part of the equation here. So dp divided by p is equal to k multiplied by dt. We take the integral of both sides, giving us ln of absolute value of p is equal to kt plus c. And then trying to get p by itself, then that means p is equal to e to the kt plus c, which I can then simplify into the following equation. C1 times e to the kt, where C1 is supposed to be e to the c then as a result. And since p is going to represent population, then we can just get rid of the absolute value. And you can see now the result is that we do have an exponential equation. So that's how we can kind of derive it in that sense using calculus. Now, the problem is when it comes to population, your growth is not actually going to be exponential, but it's rather going to be something called logistic. And in terms of what that means, or how do we translate what's the meaning of logistics, if you're not like one of those science people, logistics growth basically says that, hey, you know what? You are going to grow exponentially at first, but then after a while, you're going to have to worry about some other stuff that will stunt the growth of the population. So for example, maybe like, say, a carrying capacity. So for example, like, say, on Earth, there's only so much space for a human to grow. And then as a result, we're going to have some sort of upper bound. So then that way, we cannot exceed that upper bound then. So in reality, the logistic growth is that you have a curve that might look like the following over here, okay? Another one that I can think of is, well, what about resources? Like, say, if you have a population within a certain area, as soon as you run out of resource, or as soon as you're running low on resource, then your population is not going to grow as fast. But anyhow, the logistic growth was going to look something like the following then. So here, let me just go ahead and sketch out the curve of an exponential growth, which looks something like this. That's how it's supposed to be. That's how ideally we would want it to be. But in reality, the logistic growth says, hey, we're going to, like I said, grow kind of like exponential growth. But then after a while, what will happen is that we're not going to follow that concavity, but rather we're going to have our own concavity that's going this way. Because again, what if we have some sort of capacity then? So this is going to be logistic growth, and this is more ideal for the population, or more realistic. Whereas the exponential growth right here, this is going to say, hey, if your population is like, say, like germs, for example, and then there's no boundary, and you're not like, inside like some sort of like, you're not confined in any way, then it'll grow exponentially in that case then. So this is basically what we're going to be interested in. Now, in terms of its differential equation, it's going to be the following over here, which is dp dt is equal to k times p times 1 minus p over m. Now, if you're wondering, okay, well, where did this come from? Because this is going to be kind of like a big stretch in this case. Like, there's no translation for this. We're going to translate that in just a little bit. But for right now, let me just kind of explain what each part means, and then afterwards we'll derive it, and then we'll, I guess, kind of like come to a conclusion as to where this is coming from. So P, just like before, represents the population. So that hopefully is okay with you guys. K is going to be a constant, and those two parts right there are going to be the same as the differential equation that we had for exponential growth right here. So you can see the K and the P there. The one thing that's different, as we said, is going to be this M over here. Then the M represents the carrying capacity. So carrying capacity, meaning the upper bound of where our curve is going to be. So in this case right here, if you can kind of see it, this horizontal asymptote that the graph is getting closer and closer to, that is going to be our M in this case. So that's the carrying capacity then, okay? All right, so with that being said, now let's go ahead and, let's see if I can, yep, there he goes. Okay, so let's go ahead and see what we can do in terms of solving for this differential equation. Now, do you have to do this every single time? The answer is no, because it's going to be pretty painful having to do this every single time. So what I'm going to do is I'm going to go ahead and derive it once, and then you get to, if you even need to, use the equation just from here on out. So in terms of solving for this differential equation, it's going to be a little bit harder because it's more than just separating variables. What we need to do is we need to separate the variables, and then afterwards you use partial fractions to split up the left-hand side. And partial fraction is a method that is left in the BC curriculum and kind of part of AB, but not by too much. So that's why it's kind of like, it's really, really painful to use, unfortunately, in this case, because you have so many variables. So anyhow, after you split up the left-hand side using partial fractions, then we're going to go ahead and integrate. And after we integrate, we're going to go ahead and solve for what C is. And we usually go ahead and say that the initial population, P of 0, is equal to some value P naught. We go ahead and solve for what C is. And then afterwards, we go ahead and try to solve for P. And you can see that this right here is just some algebra procedure in order to get to the end result. So in the very, very end, this is what you're going to get. So feel free, if you need to back up or pause the video just to see the procedure, that's totally fine. But again, in terms of do you ever need to derive this equation, the answer is no, because in the end, you can just go ahead and use this equation then if it's even called for, okay? So let's not, think too much about like what the equation is, but rather let's try to translate dp dt. Okay, let's try to translate dp dt. Like, where is this equation coming from, and what can I get out of it, rather than just solving for the equation? Because getting the equation is nice, but that's just a lot of as we say in class, masturbation, and we don't really necessarily need it. Okay, but instead, let's think about what does this actually mean? Okay, so here's how I'm seeing it. We said earlier that logistic growth has to look something like this, because what we're going to do first is we're going to start off kind of like an exponential growth, but then somewhere in the middle, we're going to have to change the concavity. So then that way it'll concave down towards its carrying capacity. One way of seeing it is that your dp dt is basically approaching towards 0 as P is getting closer to M. Okay, your rate of growth for your population is going closer and closer to 0, eventually getting to 0, when your population is going to M then. Okay, so that is one of those conditions that I would like to implement into my differential equation. At the same time, my dp dt is equal to 0 when P is equal to 0, or when P is equal to 0. So meaning that I have kind of like an upper bound for a horizontal asymptote, or end behavior, if you want to call it. And then you also have a horizontal asymptote at P is equal to 0 and P is equal to M. So if we were to, graph this out on a different axis, and in this axis, let's look at it as the independent variable as P, and then your dependent variable as dp dt, right? I want to see what's the relationship between the two according to what we just said. Well, when P is equal to 0, dp dt is equal to 0. When P is equal to some value M, then that means that dp dt is also equal to 0. Everywhere else is going to be positive in between because you have a growth, so therefore population has to be increasing. So the only graph to me that makes sense according to what we just graphed right there is something that's quadratic. A quadratic that looks kind of like this right here, right? Where, like we said, that dp dt is equal to 0 at 0 or m. And hence, that's where we came up with this equation over here, right? So that's where it's all coming from. Okay, so now that we understand where the differential equation is coming from, let's see if we can kind of translate or make sense of all of this. So then that way we don't have to just solve for the population equation every single time. Okay, so here is a problem using this setup right here. Suppose that a population P of t satisfied the differential equation over here, so dp dt, that's given to you, where t is measured in years then. So we have everything that's all set up. So we're given the differential equation, and we're given the initial population in this case. I want to know what is the carrying capacity for this equation then. Use this to create the slope field. So here, let's go ahead and see if we can solve for the carrying capacity. Now remember, the carrying capacity is when the derivative is equal to 0 because once you reach that carrying capacity, I don't want the population to grow anymore. So what I'm saying is go ahead and literally set it equal to 0 and try to solve for it. So 0 is equal to 0.4p minus 0.001p squared. Okay, we can go ahead and factor out some values over here. So 0 is equal to 0.4p factored out from both terms, and that's 1 minus, and if I were to put this on a calculator, which I'm doing now, 0.001 divided by 0.4, that's going to give us 0.0025p. Okay, now using this factor form, we can solve for what p is equal to. So p is equal to 0, just as we said earlier. And then for the other part, now if it helps, let me kind of rewrite this as a fraction so you can see it a little bit better. 1 minus 1 over 400p, and that is also equal to 0. So you can see now p is equal to 400 in this case then, okay? And once we have those two, we're pretty much good to go because as we said, we're going to go ahead and draw the slope field for this. So t is your independent variable. dp dt is going to be over here. We have the, we have the equilibrium solutions, and equilibrium is basically when you have the horizontal asymptotes at 0. So here's the bottom horizontal asymptote, and here's the top horizontal asymptote at p is equal to 400 and p is equal to 0. And right there, we are now just going to draw kind of like a generic slope field to show you how that actually is going to look like then. So your curve is probably going to increase, right, at first. And then afterwards, it's going to get steeper. And then afterwards, it's going to get even more steeper to a point of where you reach kind of like the middle where the population is equal to 200. At that point, that's where you're going to hit your critical population growth, like your fastest population growth. And then as a result, you're going to start slowing down then. Okay. Now, can you actually plug in values in this for p? The answer is yes, but I figure, this idea of logistic growth, you can kind of sense as to what the curve is going to look like according to what we just said earlier. So now if we were to put in the p is equal to 50, then you can probably get a sketch that the population is going to do something like the following then. Okay, so all they're asking for is just a sketch, not something that's accurate. And if you want more accuracy, you can probably use Euler's method in this case. Okay, so there's the sketch of the curve. Now, what I want to do next is I want to find out what is p prime of 0. What is p prime of 0? Now, just to make sure you guys are understanding what that means, p, right, dp dt, p represents the population, so dp dt, which is in this case, solves for the rate at which the population is growing. So all you have to do is figure out what happens when p is equal to 0 then. Okay, so literally I'm going to go ahead and plug in p is equal to 0 into this equation. If p is equal to 0, right, because that's going to be our independent variable, okay, then p prime of 0 is equal to 0.4 times 0 minus 0.01 times 0 squared, and that is equal to 0. So in this case, that's kind of like a another scenario. If your population, right, in this problem, it says if your population is 0, you're not going to grow at all. And so what that means is over time, you're using that same horizontal slope. And so you're going to actually stay on this bottom horizontal line. If you don't have a population, you can't have a growth. You have to have something to basically work with then. So that's going to be this scenario over here. Okay. All right. Next, at what population is the rate growing the fastest? Well, I want to know basically now, where is it when dPdt is going to be the largest? Okay, where is it that dPdt is going to be the largest? So then what we can do is we can go back to our differential equation over there, right? So dPdt is largest. So that's where we're solving for. And as soon as I say where is it that you have the largest, you should be thinking about where is it that you're having the maximum. So that means you're going to take this equation and solve for its derivative and solve for when what the critical point is going to be. So dPdt, if I solve for its derivative with respect to p, right, because that's going to be my equation, that's going to be equal to, so this equation right here, let's go ahead and solve for the derivative then. So that's going to be 0.4 minus 0.002p, and I'm going to set that equal to 0. Factoring out the 0.4, actually I can just go ahead and move everything to one side. So 0.4 is equal to 0.002p. So p is equal to 0.4 over 0.002. And that's going to be 400 over 2, so that's equal to 200. And hopefully that does make sense, because earlier we were saying that when your population reaches half of its critical point or a carrying capacity, that's where you're going to have the steepest slope. So that right there is just verifying it. Okay. Now, the last part is, when will the population reach 50% of its carrying capacity? So now I want to find out at what time are you going to reach that 200 for population. So this is the time where we're going to go ahead and use this equation that is derived earlier for you guys. So we're just going to literally plug everything in as is. So if you recall, P is going to be equal to 200 in this case, and that's going to be equal to M, which is 400 because that's the carrying capacity, divided by 1 plus, now this part's a little tricky, M minus P naught, so that is going to be 400 minus 50, all divided by 50 because P naught, the initial population, is 50, multiplied by e to the negative k multiplied by t. In terms of what our k value is, we're going to have to take our differential equation, right, dp dt, which is going to be this guy right here, right, and write it in the form of what we want, which is to match up our differential equation. So dp dt, if you remember, is equal to k times p times 1 minus p divided by m. So I need to factor out a number, and whatever that number that's factored out is from both terms, that's going to be my k. So in this case, it's going to be 0.4, and then we have p right here. So let me go ahead and change that first. So 0.4 factored out, and then p is also factored out, and then we have now 1 minus 1 over 400, if you remember correctly, and that is going to be my equation. So in this case, k is equal to 0.4, and then multiplied by t. So you take this guy and throw it all into the calculator and solve for it, and you would then get your answers for t in this case. So just to kind of clean everything up, we're going to go ahead and multiply it out. So 1 plus, looks like it's going to be 7 times e to the negative 0.4t is equal to 2, because I'm going to cross multiply. Minus 1 from both sides, so 7 times e to the 0.4t is equal to 1. E to the negative 0.4t is equal to 1/7. So negative 0.4t is equal to ln of 1/7. And so t is equal to ln of 1/7 divided by negative 0.4. And that, if I remember correctly, is like 4.82 or something like that. So that's going to be in terms of years. All right, so thank you so much for watching for this. And as I said, for this start here, you're not going to be, solving for any kind of like antiderivative that's nasty, but rather your job is to translate what the differential equation is actually saying, and then figuring out what's happening with the curve as a result, which is a lot easier than having to do all the nasty calculus. All right, so I will see you next time. Have a good one. Take care. Bye-bye.